So, very good afternoon, all of you. This is the sixth section of our faculty development program. So, we have a very eminent and experienced professor, uh, retired professor, Dr. N. Rajan Babu sir, to handle the section on nonlinear dynamics and chaos. So Dr. N. Rajan Babu sir completed his BTech in electrical engineering from NSS College of Engineering, Palakkad in 1982, and MTech from NIT REC Calicut in instrumentation and control engineering. Later he did his PhD from instrumentation engineering from IISc Bangalore. So he worked as a professor in the Department of Instrumentation and Control Engineering, NSS College of Engineering, Palakkad, and he has published a number of papers in the area of nonlinear system dynamics and control. Uh, he's a retired professor and head of the department, instrumentation and control engineering department. He also served as a head of the department in the electrical engineering department, MES College of Engineering, Kutipuram. So I welcome Dr. N. Rajan Babu sir to handle this section. On behalf of the coordinators and entire participants, I welcome you, sir, to handle this section. Welcome you, sir. Over to you, sir. You can handle.
Okay, let me start from the beginning. See, we are going to discuss the topic introduction to nonlinear systems and chaos, nonlinear dynamics and chaos, rather nonlinear dynamics and chaos. See, what is the speciality of nonlinear systems?
The PPT is not visible.
It is not visible. Okay, I hope it is visible now.
Yes, sir. Yes, sir. Okay.
Okay. Let us look at this root locus plot. Uh, it is designed. It is the root locus plot of a linear system. See, having a component amplifier. See, you know that amplifier saturates. What happens when an amplifier saturates? Its gain decreases. So when the gain decreases, the overall K of the system decreases. So the the system which was designed to have the dominant closed loop poles here will now move to the right, may move to the right hand side because the K decreases. So the system which was assumed to be stable now becomes unstable. That is the reason why we need to analyze nonlinear systems separately. Now let us start with the linear system. ശരിയല്ലേ? The state variable model is x dot is equal to x plus du, y is equal to cs plus du for a single input system. We get the trans function as this equation. That means trans function is the denominator of the trans function is determinant of si minus a. I hope these things are familiar to you. So determinant of si minus a equal to 0 is the characteristic equation, and the solutions are the age values of the matrix A or the poles of the system. Now, linear systems, this is a typical second order system. We have the differential equation like this, and when we model it, we get x dot is equal to ax plus du. This is a homogeneous equation, so we have x dot is equal to ax, a equal to this. Uh, the state equations to 0. X dot is equal to ax equal to 0. What are the equilibrium points? The points at which the states are stationary. So for linear systems, since the elements of the A matrix are constants, we get origin as the solution of the system. Origin as A matrix. When they are complex conjugate with negative real parts, the equilibrium point, the origin, is a stable focus. When it is a stable focus with negative real parts, complex conjugates with negative real parts. When they are imaginary, that is, the eigenvalues or the poles are on the imaginary axis, it is a center. The system is oscillatory, so the trajectories or the phase portraits, phase trajectories will be centers. When the poles, a second order system, you know there are two poles. One is negative and the other is positive. It will act as a saddle point. The equilibrium point will act as a saddle point. So this is the behavior of the system about the equilibrium points for a linear system. We have shown the node, focus, center, and saddle point. See, when we come to nonlinear systems, what is the difference? The output having nonlinear relationship with input. Systems which doesn't obey superposition principle and homogeneity. The study of dynamical behavior of the nonlinear systems is known as nonlinear dynamics. A typical nonlinear system can be represented by x dot is equal to f of x. You know, all of you know this. I hope that is why I am going a bit fast. So, what is this f? F is a function. F is systems. In our beta curriculum, we have two methods. One is the discrete function method, and other is the phase plane analysis. What is the difference between these two? Describing function is based on a transform function approach. Here we do not disturb the system. We separate out the nonlinearity and harmonically linearize the nonlinearity and apply the Nyquist stability criterion. That is why we analyze the nonlinear system through describing function analysis. Coming to the phase plane, you know that what is a phase plane? It is a state variable representation. What are phase variables? Phase variables are state variables when one of the variables is a system variable. Phase plane means phase plane, phase space or phase plane. When you come to third order and higher order, it is phase space, and when it is coming to second order system, it is phase plane. So the name itself, we know that it can be applicable to phase plane means it is a second order system. What we do, we reduce the model of order of the system to second order, and we don't disturb nonlinearity. The description, there is error in the phase plane, we don't disturb it, and the system is reduced to second order phase plane. But with the availability of computing facilities, we can treat each of the nonlinear systems separately. See, one method is to study the equilibrium points. A fundamental difference between a linear system and nonlinear system is that a linear system has got only one equilibrium point. We will see as we go further that the A matrix will not be, the elements of the A matrix will not be constant. Rather, we will have polynomials in fact. So we get more than one equilibrium point. So the each equilibrium point will have to be analyzed separately. How do we do that? We linearize the nonlinear system about the equilibrium point. How do we do that? We consider x is the equilibrium point. See, we define a new variable x bar, which is x minus xc. So we get x bar dot is equal to a into x bar. Why? All the higher order, see, we are in the neighborhood of the equilibrium point, and x minus xc, the powers of x minus xc are very small and they can be neglected. So the system becomes a linearized system around the equilibrium point or about the equilibrium point. The same can be analyzed. The result F2 etc. with respect to the respective state variables. By F1 by F2, by 2 by F1 and by F2. So we consider a second order differential equation, which is nonlinear. Why nonlinear? Due to the presence of this y2. This is a typical nonlinear system. This is called a Duffing oscillator with a nonlinearity negative. When it is positive, it is called a hard spring. When it is negative, it is called a soft spring. So defining x1 is equal to y, x2 is equal to y dot, we get x1 dot is equal to x2 dot. See the second equation? It is a polynomial and it is nonlinear. So what is J? Dou f1 by dou x1, 0, 1, you get this. Substituting a1 is equal to 2 and a2 is equal to, a1 is equal to 2 and a2 equal to 1. we get with this you have to check. I think that is A1 is equal to 2 and A2 equal to 1. We get the following equations. See, what are the equilibrium points? X1 dot equal to 0. That means X2 is equal to 0. X2 dot equal to 0 means X2 equal to 0. You have already got it. So minus A2. A2 is 1. X1 cube minus X1 cube minus A2. X1 you have to take the derivative, partial derivative, no? The derivative minus A2. A2 is equal to 1 plus, what is it? X1 2 X1 cube minus equilibrium point. The equation is X2 equal to 0. X1 cube minus A2. A2 equal to 1 minus X1 equal to 0. So this solution is X1 equal to 0 and X1 is equal to plus or minus 1. So what are the equilibrium points? 0 0 minus 1 0 and 1 0. So at 0 0, what is the J? J equal to 0 1 minus 1 minus 2. You evaluate the J at the equilibrium point. The eigenvalues are minus 1 and minus 1. What does it mean? Both are real and negative. So the equilibrium point is a no. At minus 1 0 and 1 0, if you evaluate, you get the same J because both are same. J equal to 0 1 2 minus 2, and you get the eigenvalues as 0.7321 and minus 2.7321, and the equilibrium points are saddle points, the positive and negative. So you get the phase trajectories like this. See, this is the minus 1 0. This is the origin. This is the this point is the 1 0. So these two are saddle points. This is a stable node. So that is how we analyze the nonlinear system. Now, Van der Pol equation. It is a nonlinear equation. And what is the speciality of this? The x tending to 1, x tending to 0, it is negative damping. X tending to 1, x greater than 1, what is it? X greater than 1, it is positive damping. What do you mean by positive damping? Energy is dissipated. So the x will decrease. When x decreases and it is less than 1 means it is negative damping. The amplitude will increase. So it will exhibit a limit cycle. So the oscillations are like this. The solutions are like this. And these are the phase trajectories. Any initial condition starting from outside 1 will end at here. Any initial condition starting from here will also end here. So this is a stable limit cycle. The Van der Pol equation is obtained, or what is the application of the Van der Pol equation? In modeling action potential of neurons in biomedical engineering, when we model the action potential of neurons, we arrive at a Van der Pol equation. Similarly, in seismology, there are situations where we get Van der Pol equation as models. Another is Duffy equation. See, the previous example, this is a typical second order equation. When we add a cubic term to this, it becomes a Duffy oscillator. It's a forced Duffy oscillator. Here you have plus alpha. Previously, I considered an equation in which it was the nonlinearity was negative. This is Duffy equation will come as a model in mass spectrometers. A Poltrap mass spectrometer has a model Duffy equation as its model, force Duffy oscillator as its model, and an inverted pendulum also has Duffy equation as its model. When the force is increased, it will the amplitude frequency response will look like this. What is amplitude frequency? When you vary the the frequency of the input, the amplitude will follow this path, and then it will suddenly jump to this, and it will follow like this. When you reverse the frequency, the amplitude will follow this path, and then sorry. So this is called jump response. It's called jump response. A phenomenon exhibited by nonlinear systems. See, when it is negative, you get the jump response like this. See, the amplitude will jump like this, and when you reverse it, it will be like this. Actually, the amplitude response, the Duffy oscillator can be modeled using the nonlinearities. The, the presence of the nonlinear term will have many frequency components in this, and if you average out the, periodic variations, you get the equations. I'm not going into the details of this. It can be modeled like this. So you get see, this is the actual response of the system. It has a fast moving response, and this is the overlap of this. This is a slow this overlap. This overlap can be traced like this. See, that is coming to the amplitude response. See, this is a stable. If you operate at this frequency, this is a stable focus. This is also a stable focus. But what about this point? This is a saddle point. So it can either move to this stable focus or to this stable center, not focus, center. This is oscillations. These are amplitude of oscillations. So this is center. These two are centers, and this is saddle point. See, that is what is shown by here. It has two two centers, So any operating point coming here will be moving like this. So that is what is shown here. So we move to chaos. What is chaos? The study of dynamical systems that are highly sensitive to initial conditions. They are also called deterministic disorder, and we will study the butterfly effect also. What are the routes to chaos? One is logistic map, the other is period doubling, the other is bifurcation. This is the growth model, the population growth. X of n plus 1 is equal to R into X of n. This is the model of the population. When R is equal to 1, R greater than 1, X gets larger, R less than 1. Obviously, R less than 1, it diminishes. So, when R greater than 1, X gets larger. When you have to limit the growth of population. See, how do you do that? Providing an additional term, 1 minus xn. So rescaling the growth measure, the new model is x of n plus 1. Previously it was r into xn into 1 minus xn. Now as x tending to 1, 1 minus xn is equal to 0. See, this is the growth. So population increases, then it decreases. So it will never go unbounded. Limited growth model. So this is the model r into xn into 1 minus xn. Now this model has got some features. Let us see that. I choose r equal to 0.25, 0.5, 0.75. These are the models. What happens? The population will start, if you start from here, it will decrease, and finally it will go to 0. Because r equal to 0.25, 0.5, that is a property of that equation. Now r equal to 1.25, what happens? It doesn't go to 0. Instead, it will settle at 0.25. An initial condition of 0.5 will finally settle at 0.25 when r equal to 1.25. When r equal to 2, it will remain at 0.5. When r equal to 2.75, what happens? It exhibits oscillations for some time, and then it will settle at another point. Now, r equal to 3.2. See, up to this, we had only one attractor, or one, the setting point was 1. Now, when r is 3.2, what happens? The population starting from 0.1 will increase, and finally it will oscillate between 2 edges. It is a 2-point attractor. What does it mean? The period doubles. See, previously there was only one attractor. Now it is two. There are 2 attractors. It can either settle here or settle here. Now r equal to 3.54. What is the feature? So it's a simple equation, r into xn into 1 minus xn. I am only varying the coefficient r. R equal to 3.54. What happens is it becomes a 4-point attractor. See the plot? Now r equal to 3.99. We cannot see how many attractors. It has become chaotic. It is not unstable. It is stable, but it is chaotic. So it is an n-point attractor. So from n, as you move on from r from one value to another, as r increases beyond some value, the n attractor will become 2n attractor. Previously there was only one attractor, then it doubled, then 4-point attractor, then 8-point, and so on. It will say 1-point attractor, 2-point, 4-point, then. So this is the, as n r increases, this is what happens. Now sensitivity to initial conditions. R equal to 3.8. See, I started from x1 equal to 0.3. That is first value of the population at 0.3. You get a response like this. Now I increased r equal to, r is 3.8, and r equal to 3.301. 2 times it. See, it is r equal to 3.99, and x1 is equal to 0.3, and x1 is equal to 0.301. I am choosing the constant as 0.399, initial condition as 0.3, and initial condition as 0.301. The blue one is 0.301, the other one is 0.3, black one is 0.3. See, there is a difference between uh, the 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 trajectory or the response starting from two close initial conditions. See, let you move further. The initial condition 3 and uh, zero point 0.3 and 0.300001. See, here too it is different. I have uh, see, I think that you can see the difference in the see very. This is a typical behavior of a chaotic system. Very two close initial conditions will give you diverging behavior as we proceed with the as the time increases. So okay, I have chosen the cycles 1 to 24, the two responses. One is for 0.3001 and other is for 0.3. So this is x1 equal to 0.3, x1 is equal to 0.3. Okay. The difference between these is scattered. They are scattered. Next one is Lorentz equations. See, Lorentz equation is the model of the atmosphere. See, this is also a nonlinear equation. A simple, it's a three first order differential equations. X dot is equal to sigma y minus x. Y dot is equal to r into x minus y. This is a linear equation. This is also, these two terms are linear, but this is non-linear, x, z. There are three variables. So z dot is equal to x, y. Again, and vz. This is a linear term, this is a non-linear term. This is a linear term, this is a linear term, this is a non-linear term. See, this is a water wheel. There are 6 buckets, and water is poured into the buckets, and the buckets have holes at the bottom, and the wheel is rotated. Suppose the wheel is remaining stationary. What happens? Water is poured into the bucket, and there are holes at the bottom. What will happen? See, here this side there are 4 buckets, this side there are 4 buckets. So which direction, which 4 buckets have less weight, the more weight, the wheel will rotate in that direction. So some of the buckets will get water, and at the same time water is flowing out of the bucket also. So what happens? At some point it will rotate in this direction, at some other point it will rotate in the other direction. So this system also can be, this is, you cannot predict in which or you if you watch it for a long period and try to observe this this behavior, you cannot find out a pattern in this. Why? It is highly chaotic. It is not a predictable system. These are called law. It is a gamma, R and D. R and D. So sigma equal to 10, D equal to 8 by 3, R equal to 28. I have chosen Z as called 0. Lorentz discovered that a wonderful structure emerges if the solution is visualized as a cycle in the season. The famous butterfly pattern. and this is the attractor. So now I will show you how these floats are generated using MATLAB. See, I will first uh, see, these are the state equations. No, I cannot write it. Simultaneously, I cannot write. Simultaneously, I cannot write it. If you're not mechanical to on. So, hmm? These are the state equations. So uh, I am choosing x1 dot equal to x2. I have this equation. X2 dot is equal to minus x2 plus x1 cube minus 2x2 minus 2x2. So what is x? This is the x matrix. X is, what is x matrix? X equal to the second element of x2. And what is x2 dot? What is x dot? X equal to x equal to x equal to x1 x of 1. I can write it as x of 1, x of 2. So what is x dot? X dot is equal to x of 1 dot and x of 2 dot. 2 dot. So what is this? It is x1 dot is equal to, what is x1 dot? x2. x2 dot is equal to this. So what is it? Minus a2 into x of 1 plus x of 1 cube minus 2 into x of 2. So I will see, the function is z dot. That is how we save the file. What is z dot? Z2. Set x dot, instead of x I have used z. Z is equal to, first element is z2, that is x2 minus 2 into x2 minus x1 plus x1 cube. If you remember that equation. Now I write the program like this: 4 k equal 1 to 10. I want to generate 10 phase plots. I am giving the initial conditions from the MATLAB command window. G input is G input 1. Then I am solving the first order, the state equations. They are first order equations by a MATLAB function called ODE45. ODE45. What is it? It is the solution of the nonlinear equation by Lenga method. I give the initial conditions from the here, and you can see what is happening. Here I give an initial condition. This is a van der Pol equation. When I start from here, it sets at peace. Instead of that, if I see here, അത് ഷെയർ ചെയ്യണോ? അപ്പോൾ അതാ വരുന്നു, ഇതേ വരുന്നു. അപ്പോൾ കഴിഞ്ഞു. ഇതിന് വീണ്ടും ചെയ്തു. പിന്നെ ഇത് സ്റ്റോപ്പ് ചെയ്യണം. പിന്നെ വീണ്ടും മാറ്റ്ലാബിലേക്ക് പോകണം അല്ലേ? ഷെയർ ചെയ്യാതെ അവർക്ക് കാണില്ല. ഷെയർ ചെയ്യാതെ അവർക്ക് കാണില്ല. The population to k into xn into 1 minus xn plot x. I give x equal to 0.3001. 0.301. ചെയ്തിട്ടില്ല, ഇത് ചെയ്തിട്ടില്ല. MATLAB ഉണ്ട് അല്ലേ? Okay, I will show you the other one. This is the Lorentz attractor. I have given all the constants, and the equation is given like this. Now, from the MATLAB, see, I have ഇത് വരില്ല അല്ലേ? ഇത് വരില്ലല്ലോ, ഈ ഫിഗർ വരില്ലല്ലോ. വരുമോ? ഇതാ ട്രാക്ക്. അത് that is why it is called a two-point attractor. One attractor is one attractor. The same is the same can be you can see that real-time mode icon. Good. Controller side okay. for different values of initial conditions, you get the population. So these are the routes and the nonlinear systems, or the uh, the singular points or the equilibrium points. Whatever. Any questions? Responsible. This is Martin.
Hello, sir.
Yeah. Yes. Eh? The connection was lost. So any this
Yeah.
the remaining few minutes, remaining time can be utilized for discussions. Any clarity on any plot or any point,
Yes.
singular points or the equilibrium points or the van der Waals oscillator or any topic related to this? I'll be happy to discuss with you. Okay, all of you are faculty members, and this is my first talk on in online. See, I belong to an old generation.
Please, Rajan.
See, I was not familiar with this. That that problem is. I know that some problems were there in the coordination. But
Facing some
yeah,
connection
tell me.
issues.
Hello. Hello. ഒന്നും കേൾക്കാനില്ല.
Okay, participant, please come up with your
See, I thought that when if I come to GEC where this meeting is this course has been organized, I thought that I could present it well, but here too I found it difficult. Okay, any doubts? Any or anything to be discussed further?
Hello, sir. Hello.
Yeah, yeah.
Yeah, sir, in the PPT, one of the slides you had shown the face portrait for inverted pendulum, or it's not face portrait, I think, a jump resonance.
Yeah, Brasnas. Yeah, it is not face portrait. Yeah.
I don't know if it was for inverted pendulum. Did you show that?
No, it is actually a Duffing oscillator. A Duffing oscillator at some point in inverted pendulum at some operating point can be modeled as a Duffing oscillator, post Duffing oscillator. Not at all operating points, at some operating points.
Okay, sir. Okay.
Actually, I have shown the phase portrait of that. I have the nonlinear equation has been averaged. Uh, and I have chosen a frequency, and I hope you remember there
Yeah.
were two. Yeah,
Yes. That
two,
yeah,
two,
that was
two,
what
two,
I.
two centers and one saddle points. No, that is
Yeah.
actually the
Yeah,
that is
I
yeah.
actually wanted some more detail in that, but is it possible to go back to that slide or is it difficult? Then it's okay, explanation would be enough.
What? Like element.
It's okay, sir. If,
No problem. Uh, no. Right, show. Yeah, this one, no.
one related to inverted pendulum you said
No. That I
that
just I mentioned
that
that
is for
inverted
oscillator.
Duffing oscillator represents the inverted pendulum at some points,
Okay.
at some operating point. Actually, the forced Duffing oscillator can be the inverted pendulum at some operating point, not at all operating points. Can be modeled as a Duffing oscillator. That is what I told you.
Okay, sir.
Any other?
If there are no other doubts, we'll wind up the session.
Yeah, I have handed over all the programs. All the plots have been generated by me. I have handed over all the programs, MATLAB programs. Some of the instructions may be new to you, that G input, where I can generate the face portraits by clicking the figures. Initial conditions can be given from the screen, from the on the figure itself, and that instruction comet where we found the real-time generation of that butterfly effect.
Okay, sir, I think if there are no other queries, we'll just wind up the day. So that was a very good informative session by Dr. Rajan Babu sir about the nonlinear systems, the dynamics of the nonlinear systems, and the chaos. So on behalf of the Department of Electrical Engineering, GMT Tissue, and the participants, I thank you, sir, for such a very informative session. Thank you, sir.
Thank you, Uma, and I thank Ramesh, Uma, Dina, and Prashant. Actually, Dina and Prashant helped me a lot. Otherwise, I could not have presented at least in this way. And this is the problem with the online lectures. Had it been a offline or a classroom session, I could have done it. The coordination between the MATLAB figures and the PowerPoint can be handled in a better way. I'm sorry for the lack of clarity in my in conveying the topic. So thank you all. Thank you, the participants. Any
Thank you, sir.
any
It's
doubts?
okay, sir. We understand.